You've scanned thousands of them, on menus, on packages, on posters, boarding passes, payment screens. You point your camera at a little black and white square and somehow instantly it knows. A website, a ticket, a payment. But look closely at one, really look. It's just a mess of dots. No letters, no numbers, nothing you could ever read. So how does your phone read it in a fraction of a second, from any angle, even when it's crumpled, faded, or half covered? Today we're going to decode the CRU code, square by square. First, the name. CRU stands for Quick Response, and it was born in 1994 in Japan, not for phones, which barely existed yet, but for cars. An engineer named Masahiro Hara at a company called Denso Wave needed a better way to track parts on Toyota's assembly lines. The old barcode could only hold about 20 characters, and it could only be read in one direction, like a single line of text. Hara wanted something that could hold hundreds of times more data and be read in an instant from any direction. The inspiration famously came from the black and white stones of the board game Go. A grid, two colors, read in two dimensions at once. That's the leap. A barcode is a line, a CRU code is a grid. So let's build one, strip away the mystery, and a CRU code is nothing but a grid of tiny squares. Each square is called a module, and each module is a single bit of information. Black means 1, white means 0. The smallest CRU codes are 21 squares wide by 21 tall. The largest are 177 on each side, enough to hold a few thousand characters. But here's the problem. If it's just a field of black and white squares, how does your phone know which square is the top left corner? How does it know where the grid begins, how big it is, or which way is up? A crumpled sticker on a lamppost could be rotated any direction. The genius of the CRU code isn't the data, it's everything the designers added around the data to make it findable. Look at any CRU code and three things jump out immediately: those big square eyes in three of the corners. These are the finder patterns, and they are the key to the whole system. Each eye is the same design, a solid black square inside a white ring inside a bigger black ring, 7 modules across. Now why this exact shape? Because of a ratio hidden inside it. If you draw a line straight through the center, you pass through black, then white, then a block of black 3 times as wide, then white, then black. 1 1 3 1 1. That ratio, 1 to 1 to 3 to 1 to 1, is incredibly rare in normal images and text. So your phone doesn't try to see a CRU code. It scans across the image in every direction, hunting for that 11311 signature. The moment it finds 3 of them, it knows this is a CRU code, and here are 3 of its corners. And 3 corners is exactly the trick. 3 points define a right angle, so the phone instantly knows the orientation, which way is up, and how the code is rotated or skewed. That's why you can scan a code upside down, sideways, tilted flat on a table. The 3 eyes always tell your phone which way to look. But the eyes don't work alone. A few more hidden structures make the whole thing readable. Running between 2 of the eyes is a dotted line of alternating black and white squares. This is the timing pattern. It works like a ruler. By counting those alternating dots, your phone figures out exactly how many modules are in the grid. In larger codes, you'll also spot smaller versions of the eyes scattered through the grid. These are alignment patterns. When a code is printed on a curved bottle or a wrinkled receipt, the image gets distorted, and these little markers act like anchor points, letting your phone straighten the warped grid back into a perfect square. Right next to the finder pattern sits a thin band of modules, the format information. Think of it as the code's instruction label. It tells your phone 2 things before it reads any data: how much error correction is built in and which mask was applied. Hold that word, we'll come back to it. And finally, that empty white border around the whole thing. That's the quiet zone, not decoration. A mandatory margin, 4 squares wide, that isolates the code from surrounding clutter so the scanner knows exactly where it ends. Now finally, the data itself. Everything so far is scaffolding. All the real information lives in the remaining squares. The data is written along a path that snakes up and down the grid, 2 columns at a time, starting from the bottom right corner and weaving around every pattern we've already placed. But how do squares become text? There's one small step your phone does first. It flips the pattern back using that mask I mentioned. We'll see it in a second. And then it reads. So let's read a piece for real. The squares are taken in groups of 8. 8 bits make 1 byte. Watch this block: white, black, white, white, black, white, white, white. Red, black is 1 and white is 0. And that's 0 1 0 0 1 0 0 0. In binary, that's the number 72. And in the standard character table computers use ASCII, 72 is the capital letter H. Do it again with the next block and you get 73, the letter I. Keep chaining bytes, and those meaningless dots resolve into HI, or a phone number, or a Wi-Fi password, or the web address that opens the instant your camera locks on. That's the whole secret. It was never a picture, it was always text, folded into a grid. Quick detour because I promised. If you encode a simple message, the raw pattern can come out lopsided. Big clumps of black here, big empty patches of white there, and clumps are a scanner's nightmare. They blur together and cause misreads. So the standard does something elegant. After the data is placed, it flips a regular pattern of squares from black to white and back, like laying a stencil over the grid. This is called masking. It scrambles the look just enough to break up the clumps and balance black and white evenly across the whole code. There are 8 different stencils. The encoder tries them all and keeps whichever makes the code most readable. And remember the format information. That's where it records which stencil it used, so your phone knows exactly how to flip the pattern back before reading a single byte. And now the part that feels like magic. Take a crew code, tear off a corner, spill coffee on it, slap a logo right in the middle, and it still works. Why? Because a crew code doesn't just store your data, it stores extra redundant information alongside it. Using a mathematical technique called Reed-Solomon error correction, the same family of math that protected data on CDs and VEDs and on spacecraft talking to Earth across millions of miles. The idea the code deliberately includes backup information calculated from your data. If some squares are unreadable, damaged, dirty, or covered, the phone uses that backup to reconstruct exactly what was lost, as long as too much isn't missing. You even choose how much protection to build in. There are 4 levels, from low to high. At the highest level, a crew code can lose up to about 30% of its squares and still be read perfectly. 30%. That's why brands can drop a logo dead center in a code. They're sacrificing squares they know the math can rebuild. So let's watch the whole thing happen the way your phone sees it in the blink of an eye. The camera sweeps the image and locks onto the 3 eyes. It reads the orientation, straightens the grid, measures its size against the timing pattern. It checks the format band for the error level and the mask. It flips the mask off, snakes along the data path reading bytes, runs error correction to repair anything missing, and out pops your text, a link, a ticket, a payment. All of that from a smudged square on a napkin in well under a second. It was never a picture you were meant to read. It's a tiny, self-correcting, self-describing document, and now you know exactly how it talks to your phone. If you'll never look at a crew code the same way again, good. That was the goal. If you want more of these, the hidden engineering behind everyday tech, subscribe, and I'll see you in the next one.